reminder of a partial order. So this totally pulls us back to when we were talking about relations. Not that we've ever stopped talking about relations, because functions were a special type of relation, just like equivalence classes were a special type of relation. This guy here, a partial order, is another special type of relation. So you've got some relation. It's going to be called a partial order if it has three properties: the reflexive property, the anti-symmetric property, and the transitive property. And just to make sure that we are all comfortable with what those three properties mean, because otherwise today is not going to go super well. The reflexive property means, actually let's just put a little bit of extra space below that guy. The reflexive property means that in your set of ordered pairs, which quite frankly we're not going to see very much in this section, you'll have all of your ordered pairs. The thing that we are going to see more in this section is on each vertex we have all of our loops. And remember, I've been calling loops the guys that, here's your vertex, and it's the directed edge, the arrow that starts and stops at the same location. Okay? So that's reflexive. You have all of those loops, all the possible loops in your picture representation. Now, anti-symmetric, this is the one that in the picture representation, if you have two different elements from your building set, you can either have no arrows between the two different elements, or if you do have an arrow between the elements, there is exactly one arrow. You're not allowed to have the arrows going in both directions. Okay. And then transitive, in terms of the picture, the graphical representation, if you pick any length to path, and for us when we say length to path, we just mean you use two arrows back to back. Anytime you have a situation like this, there is always, if you have the transitive property, a single arrow existing in your picture representation. That is a shortcut where instead of picking two arrows to go from vertex C to, vertex A to vertex C, instead you do it in one jump directly A to C. Okay. So that's things that we need to know about our properties: reflexive, anti-symmetric, transitive. Now we're going to do stuff on partial order, which means we always have these three properties if we start off with our partial order. And our starting point is going to be we have partial orders. Okay. Now, first couple of examples is just some examples of guys that are partial orders. So we'll check to see if they actually are a partial order, and then we'll see some classic examples of guys that are partial orders. Now, the thing that we're going to care about is something called a partially ordered set, or poset for short. It's sort of an acronym. It's not POS. We do actually have the set here, but the P from partially and the O from ordered are abbreviated there. Okay. So this guy here is focused mainly on the building set, and it's the set together with your relation that's a partial order. And in terms of notation, there's actually a lot of different standards for the notation for a poset. One of the classic ones that's relatively a generic sort of notation is what looks like an ordered pair, where the first guy in the ordered pair is the set you care about, and the second guy in the ordered pair is what the relation is. Okay. There are other ways to represent these posets, and for famous posets, they actually have names. So when we get to famous posets, I'll actually show you the shortened name. Do you have to remember that? Probably not, because normally on the things that I'll give you, I'll also write out what the description is too. Okay. So let us look at an example. So I've got several examples prepped up for us here, and the first example that I've got prepped up for us here, and let me actually just make it so you can see the example, is this guy. Our building set is the integers 1 through 5, and the relation defined here with our ordered pairs is you're going to grab your ordered pairs exactly when the first position of the ordered pair is less than or equal to the second position of the ordered pair. And what we would like to check is this guy actually a poset? Now, when we say poset, we're referring to the set in conjunction with the relation. So the thing that you check to see if you have a poset is you're really only focused on the relation and checking if that relation is actually a partial order. Okay, so we'll do that here. So sort of a first step would be, is R a partial order? So the first thing is you check to see if it's reflexive. What do you think? does this relation here look like it would be reflexive? And we can write out the ordered pairs too, but just looking from the formula, what do you guys think? Does it look like it would be reflexive? Would it have all of its ordered pairs A, comma, A? What do you guys think? Yeah, it should. And it should because why? In the formula right here, you've got the first position is less than or equal to the second position, so that tells you that you can totally have A to be equal to B. Well, if you have A is equal to B, that gives you your doubled up ordered pair of the A, comma A, which is exactly what you need for reflexive. So the answer here is yes, it is reflexive. And this is because A, comma A is inside of R. Notice here, A equals A meets the inequality or really less than or equal relationship that we have. Now, second thing that you check for a partial order is anti-symmetric. So the issue here with anti-symmetric is, well, how would we check if a relation is anti-symmetric? And it would be dealing with this. So suppose we actually have A, comma B inside of a relation. Notice what that means. That means that A is less than or equal to B. Now, since we already know the relation is reflexive, let's go ahead and assume that A and B are different. Okay? So I'm going to put a little slash there through the equals part just to say, hey, A and B are different. So our question then is, can we reverse the order? Did not mean to write a line there. So what do you guys think? If we have the ordered pair A, comma B is inside of your relation R, that means A has to be less than B. Could we ever also at the exact same time have that element B is less than A? What do you guys think? And remember, our little A's and B's are only the integers 1 through 5. Yeah, no, that's not possible, so I'm going to put a slash through that. And what that tells you is that the ordered pair B, comma A would never be in your relation if you already had the reverse of that. Okay? Notice you can do all of the same thing by just writing out your ordered pairs. Our building set is small enough that you could totally just write out your ordered pairs. However, if this building set A was actually all integers, what we're doing right here would be the only way you could check to see if your relation is actually anti-symmetric. So what that tells you is if you're only allowed to get one of these two ordered pairs at most, that means we're going to be anti-symmetric. And then we'll check if we are transitive. Okay? Now this one here, we first check to see if we have two pairs of ordered pairs in our relation. Now, what that means according to our formula is that A is less than or equal to B, and that we also have B is less than or equal to C. Now, according to transitivity, we're trying to get that A is related to C. So what do you think? From these inequalities, do we actually get that A is less than or equal to C? Is that a true logical deduction here? What do you guys think? Yeah, definitely. This is something we do all the time with integers. You string a bunch of inequalities together. So that tells you that A, comma C definitely should be in this relation as long as you started with these first two ordered pairs being in your relation. So that means you are also transitive for this relation. Therefore, yes, our answer is yes, R is a partial order because all three of those conditions were met. Yay, we got what we wanted. Now, follow this up. If we actually care about whether somebody's a poset, the answer now is immediate, and we get that A, comma R is a poset. And the reason we know that is because R is a partial order. And that's how to check to see if somebody actually is a poset. Literally, the only thing you are checking is that you have a partial order on your relation. Okay, questions? All right, let us look at another example. So this here is the example we just did. Is the quintessential example of illustrating what a partial order is. It's this less than or equal to symbol. And in fact, it's so incredibly quintessential, so incredibly this is how partial orders were put together, that one of the ulterior ways of writing a partial order is actually like this. You put whatever your set is, and then you have the symbol less than or equal. And that's actually a shortcut way of people saying, hey, you've got a partial order for your relation. Okay. Now, that's one of the really, really classic examples of a partial order. Here is another really, really classic example. And notice, in terms of your relation, it actually is really, really similar. Okay. The symbol here is not a less than or equal to symbol, but if you sort of close your eyes and squint, it kind of looks the same. It is the subset symbol. So here's how to read this all out. Our building set here is our power set of the set AB. So let's actually write out what that is, unlike what we did last time. So for this one, we have the empty set is a subset of AB. And remember, power set is what? It's the list of all your subsets. We also have a subset with one element. Now, we've done this before. What do you guys think? What's another subset of the original building set AB? And you either look in the exponent here or inside the parentheses for your original set. What do you guys think? What's another subset of that building set AB? You got it, just a single element B. And there's one more. Anybody remember what the last one is? Or can see it straight up even if you don't remember? I think we actually did this exact example ages ago. Turns out the last set is the very first set, the empty set, and the very last set are the two that people have a tendency to forget. The very last subset is actually the full complete set, and that is because the power set is a list of all subsets, not just proper sets. And remember, these first ones are proper subsets, meaning they're legitimately smaller than your given set. This is the only subset that's not a proper set. It's the full set. Okay? So these are our 4 elements that we're looking at. In terms of the relation, notice what it says. It actually tells you that your ordered pairs, the first position and the second position, are coming from your building set. So you've got ordered pairs like this. Empty set, comma, empty set. Empty set, comma, one element set. Empty set, comma, other one element set. I'm not going to write them all out, but you also have one element set A, comma, the full set. And we actually got to there's a few more. So that's what those ordered pairs look like. So very different in terms of the individual elements. Notice structurally how we put this together. The first position was the set that was inside of the other set, so a proper subset. Notice an ordered pair that wouldn't be in here. You wouldn't have the single subset just of an A, comma, single subset just of a B. That one would not be one of the ordered pairs in here because A is not a subset of B. Okay? So this would be this relation here. Now for this guy, it turns out it's also going to be a partial order. Reflexive, yes, every set is a subset of itself. So you would get all of these guys for reflexive. For anti-symmetric, if you've got somebody who's a subset of someone else, if you reverse it here, so I'm picking on this element right here, or this ordered pair that's empty set, comma, just the singleton set A. If you, empty set is a subset of set A, but if you reverse it, set A is not a subset of the empty set. And the only time that you can reverse it is if you're in one of those reflexive element situations or ordered pair situations. Okay? So that would give you anti-symmetric. And transitive is very similar to what we did with the less than or equal symbol. With a subset symbol, you can link together things. So for example here, if you've got the empty set is what is a subset of A, and you have A as a subset of AB, well, you can link these guys together and get that empty set is a subset of AB, and that would give you your transitive property. Okay? Now, notice what this tells you. This does tell you that if we put these two guys together, so if we look at the original set that's all of our subsets of AB, in conjunction with this partial order, we've now created another very classic example of a poset. So let me write down what we just said. So R is also a partial order. So this means that A comma R is a poset. And this guy actually is fancy. It has its own name. This guy is actually by name B2. I don't care if you remember that part or not. Okay? But just giving you what those names are. Now, let us see some of the things that we can do with posets once we have a poset. Okay? So the first thing that we typically do is instead of writing out all of the ordered pairs or trying to throw this into the matrix representation, all of which is something you can do in a partial order because it is a relation, at least as long as you have some sort of finite set. Infinite set, you got to play around with it a little bit more. We typically look at the Hasse diagram of a poset. Now, the Hasse diagram is a graphical representation, so it's a picture. It looks very, okay, it does not actually look very similar to the Digraph representation that we've done previously, but you can build the Hasse diagram from that original Digraph representation of any old relation that we were dealt with previously. Okay, so the first example that I've got prepped up for us is both the method of how to create a Hasse diagram from a given digraph of a relation, and then we're going to see how you can jump straight to the Hasse diagram without going through all these intermediate steps. So, first thing is our method. So the method of creating your Hasse diagram from your digraph of your original relation, you start off and you get the digraph. Okay? Once you have your digraph, since every single poset is built from a partial order, we know that all of these guys are going to be reflexive, so we remove all of our loops right here. Now, why is it okay for us to do that? Because we already know this thing is going to be reflexive. This is because all partial orders are reflexive. So it is like if you are dealing with algebra, some sort of algebraic expression, and you have a 1 times an x. Do we write 1 times x? Yes, some of us do, but it's also perfectly fine to just write plain old x. Do we know the 1 is there? Yup. It's understood that it's there, but we're not explicitly writing it because 1 times x or just x, that 1 is always implicitly there. That's that same sort of idea of removing all the loops. Because partial orders are always reflexive, we know in our heads it's there, and we're just going to be too lazy to actually write it out. It also, one of the big points here of the Hasse diagram is it declutters your digraph. Remember on our digraphs when we've been drawing them, sometimes they can get really snarly, and the only reason most of our examples haven't gotten crazy with all of the arrows and loops, etc., is just because they've been so small. We're about to get into relatively small examples for posets, but in terms of the digraph, they're going to have tons of little snarly arrows. Like, for example, 20 plus arrows on a relatively small number of vertices. It's too much information to read easily. So that's one of the points of making these Hasse diagrams. Now, the second thing that you do is you remove all, for lack of a better term, transitive edges. So here's what a transitive edge is, and let me actually put this in a different color so it's easier to see. So here, if you've got your A, you've got your B, you've got your C, the transitive edge, so the edge that we would remove, is the shortcut edge. Okay? So when we deal with digraphs, what do? We actually are looking at where every individual arrow can travel in a length 1 path and a length 2 path, and we're very careful and precise about how many of those arrows we travel on. In the Hasse diagram, we're not careful and precise about how many arrows we travel on. Instead, what we do here is just, can we follow the arrows to get from one vertex to another, and it doesn't matter if we do it in 1 step or 2 steps. So what we do to declutter the picture is the shortcuts, we remove them and assume that if you can follow any path to any other vertex, you could have actually done it in 1 step if you wanted to. Okay? So that's removing the transitive edges. And the last thing that we do is we reorient how the vertices are on the page. And specifically, it's so that all of your directed edges, and remember, directed edges are the exact same thing as arrows, so that all of your arrows are pointed in an upwards direction. Sometimes those arrows will point exactly up, so you'll get little vertical arrows, but more frequently they actually are just slanted upwards, like this little diagram right here. As long as they're pointed in an upwards direction, you're good to go. Okay? And the reason that we need to direct it so all the arrows are pointing upwards is the arrow gives you the direction of the edge, and what we're about to do is change our arrows from arrows into just straight lines. So the symbol that we used previously with the arrow to indicate which way you travel along that edge is now getting removed. So in terms of the Hasse diagram, it's always travel bottom to top is the correct direction along your edge. Okay? So this orientation then tells you how to travel along your edges. Now, that is the crash course on how to convert a digraph from any old relation into a Hasse diagram. And when I say any old relation, this only is applicable if you start off with a partial order. So you take the digraph of the partial order and then convert it into a Hasse diagram. So let's actually see what this would look like with respect to an example. And the example that I've got prepped up for us is a really, really tiny example. Our building set here is just the elements A, B, and C, so it's only going to have 3 vertices in the digraph. And in terms of the actual edges or arrows in the digraph, we have AA, AB, AC, BB, BC, and CC. So first thing is, let's go ahead and draw out what the digraph is for this guy. And let me label what I'm doing, and then we'll have different snapshots at each stage. So our digraph representation, and I'm just going to throw these vertices on here in no real particular order. We've got AA, so we've got a loop at A. We've got AB. We've got AC. We've got BB, so a loop at B, BC, and we've got CC. And this is almost the smallest partial order you can have. Note here to the side, this guy is reflexive because we have the loops on all of those arrows. This guy is anti-symmetric because notice if there's an arrow between 2 different vertices, there's exactly one of them. And it turns out it is also transitive. Here, the only length 2 path we have that doesn't include loops, A, B to C. It does have a shortcut from A to C, and if you are including 1 or more loops in that length 2 path to check for transitivity, it's automatically going to work out, which is why I only checked the length 2 paths that did not include the loops. Okay. So this guy is a partial order. So R is a partial order. Once you've established that R is a partial order, if you're not told that explicitly in your problem, then you're ready to go ahead and go through this 3-step process to convert our digraph into a Hasse diagram. So the first thing we're going to do is we're going to remove all of the loops. Okay. So remove loops. So notice same exact picture, except now all of our loops are removed. So it just looks sort of like a triangular type shape, except I reversed the arrow. Don't reverse the arrow. There we go. Okay. Now, second step, and let me pull this down so we can see our second step. Second step is to remove all of our, and this is a descriptor, not a real name, all of our transitive edges. And remember, that meant we're removing these edges that are currently indicated in orange in the little diagram, find any length 2 path, and remove the edge that was the shortcut. So if we look in our picture, who would be tagged as our transitive edge? You've only got one of 3 choices for a potential transitive edge. Anybody got a guess? Ooh, for a name of an edge, you need both the starting and the ending arrow. So if you just say the B, I don't know which edge you're thinking. So what do you guys think? Yep, A to C would be our transitive edge. So let me go ahead and highlight this guy. That one right here is our transitive edge. And we know it's our transitive edge because there's only one length 2 path in this graph that's left. Notice we removed all the loops, so we don't even have to have them clutter up the idea here. So length 2, A to B to C. The shortcut was just A to C. Notice there's no other length 2 path in this adjusted digraph. So next step, remove transitive edge. If there's more than one, remove all of them. So in our case, we'll still have A, we'll still have B. Keep all of your vertices, and we're just going to remove that highlighted edge. Okay. Now, last thing to do is you reorient. So redraw. I don't think that's how you spell reorient. So I'm just going to say redraw. How? We want all of the arrows to be pointing up, and then we're going to remove the arrow heads. Okay. So if we wanted to redraw this for all of the arrows pointing upwards, who would be the lowest vertex in the new picture or the new orientation? In other words, if I start drawing and I start drawing from the bottom of the picture up, which vertex should I pick on first or draw first? Don't overthink it. Ooh, overthinking it. So you want the arrows pointing up. So at the bottom of the picture is not going to be C. C will be at the top of the picture. Why would I say C is at the top of the picture? Because you got an arrow pointing to C and the arrowheads had to be pointing up. Now, it actually doesn't matter if you start at the top or the bottom of the picture, so we could totally actually backtrack and go top to bottom. So below C would have to be B. Why would I say B? Because it's follow the arrow backwards. And below B would have to be A. Now, that's not the final answer. The final answer, or the actual Hasse diagram of this particular original poset, would be C, no arrow, B, no arrow, A. That procedure will work every single time to convert a digraph of a partial order into a Hasse diagram. Now, that being said, I wouldn't recommend it most of the time, but that method will actually work every time. Okay? But that's attempting to get you the idea of the pieces and parts that we're going to be removing from the digraph to get only essentially like the skeleton. Actually, skeleton is a technical math term that refers to something a little different. But it's like getting the underlying structure that you need to see how the elements of the set interact with each other without all of the extra superfluous stuff. That's sort of the idea behind the Hasse diagram. Okay? Questions make sense, could follow it a little bit. We're at least okay if I did it. Seeing no questions come through, I'm going to assume that was a yes implicitly on all of your guys' part. So let us look at a definition, actually two definitions here. The first definition is something called comparable. Comparable deals with elements. So if you take your poset and you take two elements from the building set, and please note when you're working with your poset, let me make sure I have a highlighting color. When you're dealing with your poset, the thing to remember is the set part of poset, because what you're going to be dealing with is you'll be dealing with the elements of the set, and then sometimes, why is it called a partially ordered set? Because that tells you that the elements actually have some sort of way to potentially compare them or relate to each other. So here, comparable elements, you take a pair of elements in your set. They're considered comparable if one of two things happen. Either A is related to B, and remember that means in terms of the relation notation, A comma B is an ordered pair, or B is related to A, and remember in terms of ordered pair notation, this was the same thing as saying B comma A is an ordered pair in your relation. Now remember, partial orders as the relations that we're dealing with here are anti-symmetric, so you're not going to have both of these two possibilities. You're going to have one or the other possibility or no relation whatsoever. Comparable means you've got the exactly one relation that you can have. There actually is some sort of relationship between them. Okay. Now, a chain is a type of poset, and it actually has a special name, C for chain, because we're super lazy. And the subscript N here tells you actually how many elements are in your chain. Okay. So a chain is a specific type of poset where every single pair of elements in the poset, or really in the set, are comparable. So everybody's related to everybody else. Now, here's why you have the naming convention. Chains look like, in terms of their Hasse diagrams, so posets that are chains, their Hasse diagrams look visibly like that physical chain that you'd have that you touch that has metal and links and stuff like that. Or I guess you can have plastic chains too, they're just not quite as useful, other than like toys and such, okay? So that's actually where the naming convention comes from. Now let's check to see if that actually works with the original partial order we saw. We're supposed to have every pair of elements in the set were comparable, so I'm going to scroll back up. Up here in our original guy, we're going to ignore the doubled up ordered pairs, the guys that turned into loops, because they're not going to matter here. But if we look at every pair of guys, we look at A, B. Yep, A and B were related to each other in the relation. A, C. Yep, A and C were related to each other in the relation. And the only other pair of elements you can pull from this set would be B and C. And it turns out B and C are related to each other as well. So this guy, just looking at the ordered pairs before looking at the Hasse diagram, by the strict definition of a chain, you are a chain. This is actually one of these smaller chains that you have, just because there's only 3 elements in the building set. Okay? So that's a special type of poset. All right. So next example, two examples, I think. We're going to be going back and looking at Hasse diagrams again, but this time, instead of attempting to draw the original digraph of the original partial order, that relation that we have attached to our set, instead we're going to try to jump straight to the Hasse diagram. Now, the 2 examples I've got prepped up here are 2 really, really classic examples. They're 2 examples of families of posets that we see a lot. Just like we talked about a name of a type of poset that was a chain, there's a lot of different posets that are chains, and all of them would look very similar in their Hasse diagram, and there's ways to actually build your chains without jumping straight to the procedure of the conversion of the digraph to the Hasse diagram we just did. Okay. But we're going to do that same sort of idea of jumping straight to the Hasse diagram in this next example. In this next example, I'm going to go ahead and just tell you it is a poset. The building set is the power set of the set 1, 2, 3. So it's all of the subsets of the set 1, 2, 3. And the relation is the subset relation. So it is, if you actually wrote out all of these ordered pairs, which we most definitely are not going to, the first position of the ordered pair would be the guy who's a subset of the second position of the ordered pair. Now, remember, we're going to be drawing a picture. The Hasse diagram is an adjusted, It's an adjusted digraph. In the actual digraph, if you have this ordered pair of BC, that corresponds to who? In the digraph, it corresponds to you having the vertex B, the vertex C, and an arrow between the 2 going from the first position to the second position. Now, what does that mean in terms of the digraph in general? That means you've got a subset, then the arrow points to the set, it's a subset too. Now, what does that mean in terms of the Hasse diagram? In terms of the Hasse diagram, that means once you remove your arrows and reorient, you are looking at the subset is below the set to subset of. Okay? And we're going to use that fact to build or place all of our elements of our building set A here first, and then we'll put the connectors in. And actually, we'll do it close to the same time. So first thing I'm going to do is I'm going to build this Hasse diagram from the bottom up. So very bottommost set is the set that's a subset of everybody else, and the set that's a subset of everybody else is going to be your empty set. Okay. One of the ways when you're dealing with sets is to order your sets by cardinality. So this is a subset that has cardinality 0. In other words, no elements in the set. Now, the next size bigger for your sets is if you have cardinality 1. So if we're looking at subsets of the set 1, 2, 3, what's a subset that has cardinality 1? Well, it is the subset of just the one element 1. Another one would be just a subset that has the one element 2, and there's one more. Anybody got a guess what the last one element subset is? You got it, the guy that's just a 3. Now, before we move to the next level up, let's look to see if there's any relationship between these guys. So between the cardinality 1 sets and the cardinality 0 sets. Okay? So or I should rephrase, are any of the subsets that are cardinality 1, are any of these guys of 1, 2, or 3 subsets of each other? So is 1 a subset of 2? Is 1 a subset of 3? Is 2 a subset of 3? Are any of these guys subsets of each other? What do you guys think? Don't overthink it. The key is remembering what you look for subsets. Yep. So the answer here is no, because when you look for subsets, if 1 was a subset of 2, the element 1 would have to be inside this second subset, and it's not. Okay? So these guys are going to be considered uncomparable or not comparable because there's going to be no relation between them because they're not subsets of each other. However, if we look below this level of cardinality 1 subsets, is the empty set a subset of any of these 3 guys? What do you guys think? Is the empty set a subset of 1 or of 2 or of 3 as subsets? And hopefully you're all thinking to yourself, the empty set has no elements in it. So one of the properties of the empty set that we saw, well, let's face it, a while back now, was that the empty set was a subset of every other set in existence. Not just the 3 that we have listed here, but any set you could ever build. So what we're going to do is we're going to put in these edges. Now, notice because I did orient the larger sets above the smaller set, that I'm not putting in the arrows right here. I'm already creating that final step, at least among these 4 sets, of the chop off the arrowhead for your Hasse diagram. Okay? If we were still in the digraph, all of these would be arrows pointing from the empty set up to the cardinality 1 sets. And that's it. That part's done. Now we'll move on to cardinality 2 subsets. So if we look at cardinality 2 subsets, you're looking at all the sets that can be built from the numbers 1, 2, and 3, where you only select 2 of those numbers. So that's exactly the same thing as if you want to count up how many of each level. This would be 3 elements, choose 2. Cardinality 1 guys would be 3 elements, choose 1. Cardinality 0 guys would be 3 elements, choose 0. That's a way to know how many of these guys you have. In terms of another one, you could have 1 and 3, and there's supposed to be 1 subset that has 2 elements left. Anybody got a guess for what that last 2 element subset would be? Yep, perfect. So the last two remaining numbers, which are 2 and 3. And remember, we're dealing with sets here, so if you reverse the order of these elements that we wrote down, it's still the same set. Okay. Now remember, we're only pulling from the original building set of 1, 2, and 3, so you want to make sure that you keep all of your elements from 1, 2, or 3. Now, once you've got the Cardinality Two subsets, you say, all right, well, I've got to connect them back to the rest of these guys, so let me see if there's any relationships between these two element subsets. And you look down at the one element subsets and notice for your two element subset of 1, 2, a subset of 1, 2 is 1. A subset of 1, 2 is also 2. Now, a subset of 1, 2 is also the empty set, except I'm going to claim that last line that we put in needs to be removed. Anybody have a guess why this last line from the set 1, 2 to the empty set really needs to be removed? What type of edge is that once we put it in? Probably should have picked a different color, but it didn't happen. Anybody have a guess why that edge needs to be removed when I'm attempting to highlight right here? Maybe I should just put it as a different color. You got it. This is one of those, for lack of a better term, transitive edges. Notice we can get from the empty set all the way up to 1, 2 by going one of two different paths. So this guy that's in orange here is one of those transitive edges that would have been removed when we built our Hasse diagram. So this is somebody we want to make sure we don't put in to our Hasse diagram. So I'm going to go ahead and remove that orange edge. It will disappear. Okay. So then we do the exact same thing with the two element subset of 1, 3. We look to see if everybody below him who is a subset of 1 and 3. Let me make sure I'm back to black writing. So 1's a subset of 1, 3, and 3 is a subset of 1, 3. And notice, just like before, we're not going to put in an edge from 1, 3 down to the empty set, because that guy would be a transitive edge again. So I'm going to get rid of that orange edge I just put in. Now, last two element subsets 2, 3. You guys, I'm going to throw it to you guys. Are there any subsets of this set 2, 3 on the level below him or two levels below him? In other words, what connections, what lines do we need to draw in here? So who should I connect 2, 3 to? Yep, we're going to connect it both to the one element subsets of 3 and 2. And just like before, we're not going to connect the subset 2, 3 all the way back to the empty set, because if we did, that would be a transitive edge. Okay? So that takes care of building ourselves up to Cardinality 2 subsets. So then we look at Cardinality 3 subsets. And if we look at Cardinality 3 subsets, well, there's only one of them because our building set that we started with is just the elements 1, 2, 3. So once you get to that full set, that's the top of your Hasse diagram. You're not going to go any further up. Now, if we look at this one new set that we've just added, all of the other 7 subsets that are currently written down are subsets of this guy. But if we so let's start with the first level. This means that 1, 2, 3 has subsets of 1, 2, 1, 3, and 2, 3. But if we put in any edge that drops down to the Cardinality 1 subsets, notice that would be a transitive edge, so we're not going to put in that orange edge I just drew in. Same deal if we tried to connect 1, 2, 3 with just 2 or just 1, all of those 3 possibilities are also that transitive edge situation. Now, last possibility that could happen is what if we tried to connect 1, 2, 3 with the empty set? Yes, the empty set is totally a subset of 1, 2, 3, but why would I claim that orange curved edge I just put in is also somebody we're going to have to end up removing? It turns out it is also one of those transitive edges, because notice, what can we do? We can travel empty set to 3, to 2, 3, all the way up to the very top there. And while it might actually travel along more edges, it is still getting us to the top as opposed to this shortcut edge. It's those shortcut edges that you remove, those guys that we tagged as quote-unquote transitive edges. So watch out, it's not just shortcuts to length 2 guys. It turns out it's also shortcuts to any length path, which is one of the reasons I put quotes around the word transitive. Although technically speaking, that one would count. It's just more than what we've talked about in the past. So let me go ahead and remove that edge. This here would be our final version of our Hasse diagram. And if you wanted to be fancy in terms of how you wrote this guy, this poset or this Hasse diagram, I should say poset, it is actually the poset, has the following name. It's actually called B3. The 3 refers to the cardinality. So this is the power set of the numbers 1, 2, 3 as a set. And the partial order that we have is what's known as ordered by set inclusion. In other words, you're comparing guys based on subsets. So this is the super duper fancy way of saying it as opposed to just AR and then you label what A and R are previously. This one is you don't name the A or the R, the set or the relation. You do this symbol that tells your reader exactly what it is. Don't care what you do, as long as in terms of what you're given here, you know how to pull together your Hasse diagram is what the main point of this example was. Okay. Questions kind of make sense, could at least follow it when somebody else does it. All right, so sets and ordering by set inclusion or having a relation where the ordered pairs are determined by subsets is super common. So this is something that you could see. Maybe your original building set is not based off of a power set, and if that's the case, the picture will look very different. If your original building set, even if it is a power set, is a different number of elements, the picture will also look pretty different too. Okay? But if you actually pull from a power set and deal with subsets, this guy is actually called a Boolean algebra, and the 3 on the subscript right there refers to how many elements were in your original building set. All right, so let us look at the other classic example, and the other classic example of a poset deals not with subsets. Yay, we're going to get away from subsets for a little bit. Instead, it deals with prime factorizations, or really factorizations. So here's the setup on how we actually write this one. Our building set is set A here, it's a bunch of integers. These are all of the positive integers of, not positive integers, all the positive factors of 18. So 18 is a factor of itself. The positive factors of 18 are 1 and 18, 2 and 9, and 3 and 6. Are there other factors of 18? Yes, but they're negative. So same numbers except negative. The relation that we're going to have is we've got our ordered pairs, and the first position in the ordered pair is the guy that's a factor of the second position. Remember this symbol over here of the A and then the vertical bar? This means, where it's read as A divides B, or if you prefer, A is a factor of B. Now, I'm just going to tell you this guy is a poset. It does turn out that this relation is a partial order. It's reflexive. 3 is related to itself because 3 is a factor of itself. It's anti-symmetric because if 3 is a factor of, say, 6, 6 is not also a factor of 3, so the order there matters. And lastly, it turns out it is transitive. If you have 3 as a factor of 6 and 6 is a factor of 18, well, 3, as you pull it up, will also be a factor of 18. Okay? So properties of factors will make all 3 of the properties for a partial order work. So once it's a partial order, the whole thing will be a poset. So what we want to do is we want to find the Hasse diagram of the poset. This poset is a pretty famous poset. Well, it's a family of famous posets. The name here is D. D for divides or divisors. The subscript tells you which number you actually started with. So this D and a subscript 18 tells you that you're looking at all the positive divisors or all the positive factors of 18, and they're going to be ordered by who divides who. Okay? which is exactly what this ordered pair of the A comma R tells you, except it's more explicit. Okay. So in this case, if we want to jump straight to the Hasse diagram without going through the first step of drawing the digraph of this particular relation, this partial order right here, and trust me, you do not want to draw the digraph of this partial order. It is a snarly mess. There are tons of ordered pairs in there, even though there's only 6 vertices that we're going to be dealing with. Okay? So instead, we're going to use a similar trick that we did before in terms of jumping straight to the Hasse diagram. Now, in this case, we're not going to be able to use cardinality because we're not dealing with sets. So here, we care about factors. So what we're going to do is we're going to look at the prime factorization of all our numbers. 1 is not prime, but it also doesn't have any prime factors, so we're going to ignore the special case of 1 and leave them alone. 2 and 3 are prime, so we're not going to do anything with them. So it's really only the last 3 numbers that we're going to look at. So if we write these guys in terms of the prime factorization, 6 is really 2 times 3. 9 is really 3 squared. And anybody happen to get the prime factorization of 18? Or you're only writing out the number as a product of primes to remind ourselves of prime factorization. Perfect. So it's going to be a 2 and then 2 3s. So 2 times 3, and I'm going to write 3 squared just because there's not quite enough room between the prime factorizations in the last example. So let me see if I can't put a little bit of space right there. Just barely. Ah! There we go. All right. So let us build the Hasse diagram. The key thing to note here is the relationship. So when we're dealing with, so scratch work over here to the side. So if we have the ordered pair, something like, oh, I don't know, 2 comma, eek, 2 comma 6. In terms of the digraph, we'd see 2, arrow to 6, 2 here being a factor of 6. But in the Hasse diagram, what do we need? We need 6 to be above 2. Because remember, we take off the arrowheads and just have the individual line. So we have to have that order that going up means we follow the arrow. Okay? Now, what does that mean in terms of our Hasse diagram? That means the guy that divides everybody needs to be on the bottom. So if we look through these numbers, what we're going to see is the guy that divides into everybody is 1. So it turns out in these type of things where you've got this partial order is using the relationship of A divides B or A is a factor of B, your smaller numbers are going to be towards the bottom. Your larger numbers are going to be towards the top. And we're actually going to order this by way of prime factors. So this one has 0 prime factors. So next level up, we'll look at all the guys who have exactly 1 prime factor. Well, those are your prime numbers, so your 2 and your 3. And now we'll do the same thing that we did with our last example. We'll check to see our relations. So we check to see, all right, does 1 divide into 3? So what do you think? Is 1 a factor? I said 3. I'm doing 2. Is 1 a factor of 2? And the answer is yes. And then you look on the other side and you say, all right, I'm looking at 3. Is 1 a factor of 3? And if the answer is yes, put in a line. Then you go the next level up. So we'll look at all of our guys with 2 prime numbers, or 2 primes in their prime factorization. And in our case, this is where we go back to our prime factorization where we did our scratch work at the top. And we see that 6 has 2 prime factors. And we also see that 9 has 2 prime factors. Please note how many prime factors you have are not counting distinct primes. It's legitimately how many primes were multiplied together. So this would be counted as 2 prime factors for your 9. So then we check to see, all right, well, which numbers below 6 and 9 are factors of 6 and 9? So if we look at 6, Prime factors of 6, or factors of 6 that are below 6, are 2 and 3. And technically speaking, 1 is a factor of 6. So what do you guys think? Should we keep that orange line that's connecting 1 and 6 together? Should we keep that orange line in the Hasse diagram? So just the way we're putting the numbers on the piece of paper or electronic version of a piece of paper, we're going to automatically get all of our arrows pointing upwards. Just by the fact that we're not drawing any loops, we'll automatically have all the loops removed. So when you're adding in edges, the one thing that you really have to worry about is not adding in too many edges, and specifically not adding in any of the transitive edges. Is that orange edge one of those quote-unquote transitive edges? What do you guys think? In other words, should we keep it or should we delete it? Yep, you guys are both right. Definitely delete it. This is another one of those sort of shortcut or transitive edges where it's totally fine. Just go 1 to 2 to 6. You get there just fine. We're not going to pull in that shortcut edge, so we'll get rid of that orange edge. Now, we'll move over to 9 and we look for our factors of 9. So if we look below 9, who is a factor of 9 that we should put an edge in? Or the number below 9 where we need to draw an edge from 9 to that number. In other words, should I put an edge from 9 to 2? Should I put an edge from 9 to 3? Which one, or both? What do you guys think? You got it. Definitely, we're going to do 9 to 3. Technically speaking, in terms, don't want orange. Orange is their indicator of a questionable edge. This one's not questionable. Okay. Technically speaking, you want the arrow head pointing to the 9, but the way I worded the question, no worries. Okay. Now, again, we're not going to put an edge from 9 to 1 because that would convert into a transitive edge. So we're only going to have one edge right here, one line right here touching 9 at this moment in time, because of 3 here is a factor of 9. I think I answered your question. If not, let me know. All right, so that takes care of all of our numbers except for 18. So let me go ahead and label what's up with 18. 18 up here actually has 3 different prime numbers multiplied together to get you to be 18. So it'll be on the next level up because it's not just 2 primes, 2 distinct primes, but a grand total of 3 prime factors in total. Now when you look at 18, you look at the first level below 18, and we notice that 6 is a factor of 18, and we also notice that 9 is a factor of 18. So we'll go ahead and put in the lines connecting 18 to 6 and to 9. Now, if we put in a line from 18 to any of the levels below, so to either 2 to 18, 3 to 18, or 1 to 18, all of those cases would actually be our transitive edges. So it turns out at this point, that's the answer. And it looks basically like a hexagon with one middle line through it. So this guy would be the Hasse diagram associated to the poset of D18. And I'm not going to lie, for this class, I have a tendency to default to these guys right here of the D and then the subscript on a number. So this would be, if you only remember one name of a poset, these would be the family of names to remember, just because you'll see them a lot in the couple days we have left for this topic, okay? Questions make sense? Feeling kind of okay, at least on how to create a Hasse diagram for the 2 main examples that we saw, which was dealing with factorization or dealing with subsets. Questions before we move on to the next thing? All right, Well, we're going to see building Hasse diagrams in almost every single example that we have in the future. Not all of them. Some of them I've got the Hasse diagram prepped up for us, and we're just going to look at specific details about it. But for a lot of the things that we do with our posets, you'll be given the poset in something like a description. You've got to create the Hasse diagram, and then maybe you're asked something about it. Okay? So let us look at the next thing, and the next thing is dealing with isomorphic poset, or what are isomorphic posets, and how do you know if you got them? Okay. So I would definitely recommend between now and tomorrow, do some practice examples with figuring out how to draw a diagram, and if you find you run into trouble, we can go back over at the beginning of next time. Okay. So isomorphic/isomorphism. I'm going to give you the really technical term, or the really technical details in terms of how to determine if two posets are isomorphic, and then we're going to look at what practically we actually do, which is way easier than that, okay? So it turns out two posets are considered isomorphic if there exists a function which is called an isomorphism between them. So here are those technical details. Suppose you've got two posets, A, R1 and B, R2. So your building sets of your two posets are A and B. Your two partial orders are R1 and R2 because I was too lazy to pick up a different name. Okay? Your isomorphism is a function. So F here indicating some function. And the domain of F is building set A for the first poset. Codomain or range of the function is the building set for the second poset. This needs to be a one-to-one correspondence or a one-to-one mapping or a one-to-one function. Mapping, function, correspondence, they all sort of get interchanged sometimes in math. Okay? Now, F is an isomorphism from poset 1 to poset 2. And we say from and to here because the domain was A and the range was B. If anytime you have A related to B, so little element A and B are related to each other in the original poset on the original partial order, that occurs exactly when in the second poset, F of A, so the element in poset 2 that the element B from poset 1 is mapped to, must be related in your second partial order to F of B, or the element that little b in the first poset was mapped to in the second poset. Okay? Then, if we have that isomorphism existing, that function existing between the two posets, we say poset 1 is isomorphic to poset 2. So that's all the official, very technical terms of what's going on. Here's what that means. Symbolically, you have an equals between them with a little tilde up top. Why the tilde up top? This means they are basically the same thing, except maybe the actual building sets that you use in the two different posets are two different things. Okay. In terms of what we actually do, it means they have the exact same structure, have the same underlying structure. Now, nice thing about posets is we have Hasse diagrams. Hasse diagrams declutter your digraph representation of your relation and makes it just looking at the underlying structure. So in practice, we don't go through all of this mess of dealing with an isomorphism, at least at this level of a class. Instead, what we can do is we can look exactly at the Hasse diagram. So what does this mean? These guys, if they're isomorphic, their Hasse diagrams will look identical. Now, there is a one change, and the one change is because their building sets A and B here could actually be different sets, your labels on the vertices of the Hasse diagram may be different, but the actual picture would be the same. So for example, if we found a poset that was isomorphic to D18 that we just drew, the actual picture itself would still look like a hexagonal shape with a line in the middle, but maybe you wouldn't have the labels of 1, 2, 3, 6, 9, and 18. Maybe you'd have different labels on each of these vertices. Okay? So isomorphic just says, hey, you basically have the exact same thing. You just put some different labels on it, but structurally speaking, all the properties that happen in that first poset totally going to occur in your second poset. It's a way to save yourself some work if you already know something about the first poset. So let us look at an example. So suppose we have the following example down here in red. So we've got two posets. One has a building set of set A, which is simply the numbers 1, 2, 3, and 6. The partial order associated with that deals with what? It deals with A is a factor of B. So ordered pair A comma B occurs exactly when A is a factor of B. So let me go ahead and write this in. So A is a factor of B. Note, this is the exact same structure of the example that we just looked at. This is actually another one of those guys. That is the capital D with a subscript. Here it's 6. 1, 2, 3, and 6 are all of the positive factors of 6. And we've ordered it by who's a factor of who. So this would be somebody else in that family that's labeled by a capital D. Now, the second poset that we have, its building set is by set B. And it has it's got the elements of the empty set, the set of just A, the set of just B, and the set of AB. And this guy is ordered by subset inclusion. In other words, the first position of the ordered pair is a subset of the second position of the ordered pair. Note, this is somebody we actually looked at previously, like one of our first examples of what a poset was. So we already showed that guy was a poset. And the special name attached to this guy is actually B2, but we already drew his Hasse diagram. No, we didn't draw his Hasse diagram earlier. We just verified that it was a poset. Okay. So our question is, we want to know if these two posets are actually isomorphic to each other. So we're going to do the shortcut method, which is we're going to create the Hasse diagrams of these two posets, compare them, and see if they look the same. If they look the same, the two posets are isomorphic. If they don't look the same, the two posets are not isomorphic. Okay. So if we look first at the guy that's D6, what happens? Our building set is the elements, or are the elements 1, 2, 3, and 6. And specifically, our ordered pairs are ordered by who's a factor of who. Okay. So what do? We're going to look at our primes. Well, we've got somebody that has no prime factorization, and that would be the number 1. We then look at everybody that has a prime factorization that includes exactly one prime factor. That would be your 2 and your 3. And we do actually have somebody that has more than one prime factor in it. 6, we know, has a prime factorization with 2 primes. I went 2 levels up instead of just 1 level up because we were so close to putting everything together. So 1 is a factor of 2. 1 is a factor of 3. Don't put in the line from 1 to 6 because that jumps levels and we don't know if it's a transitive edge or not. So then going from second level to top level, 2 is a factor of 6. 3 is a factor of 6. Now we can come back and evaluate, is 1 a factor of 6? Yes, but if we put it in, it would be one of those transitive edges. So we are done with this Hasse diagram. So this would be the Hasse diagram of D6. Now, if we look at building the Hasse diagram of B2, our building set B was dealing with the empty set, the single set of A, the single set of B, and the 2-element subset of AB. And here, all of our guys are ordered by subset inclusion, which means what? We can look at who's a subset of who, or specifically we said we ordered this guy by cardinality. So we have one element that has cardinality of 0. We have 2 elements that have cardinality 1. So those are the guys just A, just B. The empty set is a subset of everybody, so we put in the lines. And then we only have 1 element left. That is somebody of cardinality 2, and this is the guy AB. Subsets of A and B are just a single A, just a single B, and also the empty set, but we're not going to put in the line from the set AB to the empty set because that would be a transitive edge. So, you guys, tell me the conclusion. What do we think? Are those two are those two Hasse diagrams look the same? Do they have the same structure? Or really the conclusion we care about, Are these two posets isomorphic? What do you guys think? Yep, they are totally isomorphic. So in terms of symbols, we could say D6 is isomorphic to B2. The isomorphic symbols look like an equals with a tilde up top. And this is because their Hasse diagrams look the same. Or let's be a little bit more precise mathematically. Their Hasse diagrams have the same structure. But let's face it, what we're actually looking for is, do these two pictures look the same? Yep, they both look like sort of squares on point or little diamond shapes. The difference, notice though, is the labels on your four vertices here correspond to whoever your building sets were. Notice also the actual partial order, not even close to the same, but structurally you get the same poset behind the scenes. Okay? Questions make sense? Kind of feeling okay. And that's it in terms of isomorphic. For us, literally you just look at the Hasse diagram and you're good. Okay? So let us look at the next thing, and I need to unzoom this for the next one. Okay? So the next thing that we want to look at is specifically components of posets, and there's a couple definitions that we need. Please switch over. Okay. So for this one here, I wasn't sure if we were actually going to get to it today. So I redid the top things. Partial order needs to be a relation that's reflexive, anti-symmetric, transitive. We've been talking about the posets and then our Hasse diagrams and isomorphic posets. They have the same structure. Okay, so that's all the stuff we just talked about. Here's the new stuff. Okay, we need to talk about, or we need to define 4 different types of elements. And the first one is a maximal element. The second one is a minimal element. The third one is a greatest element. The symbol for this one is 1 with a hat. Your book calls it a maximum element, which is also perfectly fine. And there's also a least element given symbolically by a 0 with a little hat on top of it. Your book calls this a minimum element, also perfectly fine. Okay? So it turns out these guys are highly related, but slightly different. Okay? So a maximal element, notice the ending right there, this tells us that if your element inside of your poset is maximal, if you have the following criteria. If there does not exist some element C such that or where A is related to C. So notice what this means if you're looking in your Hasse diagram, because I'm not going to lie, these guys, all 4 of these types of elements are easiest to see in your Hasse diagram. If you have this element A, this means that there is maybe guys below him. I don't care who's below him, but there's nobody up here above him. Okay? In other words, you go up and you can't go up any further. That's your maximal element. Any guesses what the minimal element would be? It's the same thing except where? You can't go any further in layman's terms. Can't go any further down. So this one, if you've got your element B, what happens, there's not going to be any other element in your building set where C is below your element B. In other words, if you try to go down, there's nothing down there. Okay? So this is, you try to walk down the Hasse diagram. Now, greatest or maximum element is very similar to a maximal element, except, well, it's a little bit different, so here's how it changes. So in terms of the greatest element, this is true if X is related to A for all elements X in your relation or in your building set. In terms of what this means is you can get to A, so here's A, from, oh, don't do the arrow in that direction. Arrows don't go in that direction. You can get to everybody else in your Hasse diagram going down, or everybody else you follow up the path to be able to get up here. Okay? And we'll see how that works in an actual picture or in a Hasse diagram. Now, least element, you can define it in almost the exact same way. Your element B is the least element if there exist x's that B is related to X, and this is for all x's in your element A. So in this case, you've got your B, and from B, you can reach everybody else. So this is all your other elements. Over here, all the other elements can be reached, but they're below A. Okay? So those are the key definitions in this section. And I can't remember if I told you which section we're in your book. Posets is chapter 10 in your book, and this one I believe is the second section in chapter 10, which should be section 55, if I remember correctly. So let us look at some examples to see if we can't figure out our maximal, minimal, greatest, and least elements. So, got a couple of examples prepped up for us. So if we look at that very, very first example, anybody have a guess? So this is the example that's got 5 little vertices. We've got A, B, C, D, and E. I'm giving you the posets here, or specifically the Hasse diagrams associated with these posets. So 3 posets that you're given their Hasse diagram. You're not asked to make their Hasse diagram. You're not asked to verify that this guy is a poset. You're already told you have posets. Here's their Hasse diagram. So in this first Hasse diagram associated with some poset, what do you guys think? Any guesses who the maximal element might be if it exists? It helps here. Blow this up a little bit. What do you think? Which one of those vertices, A through E, might be a maximal element? Don't worry, I can wait. So that is going to be one of our, but maximal. So think about what you were thinking when we say maximal. Maximal deals with, let's go back up a little bit. Oh good, all of it showed up. So maximal elements is the element where you can't go any further up in the Hasse diagram. So key thing with maximal element, you can't go any further up. So that would be, yep, A would be a maximal element of the very, very first Hasse diagram. Why? Because, bam, you can't go any further up from A. Now, if we wanted the minimal element is the one that you can't go any further down from. Now, you don't normally travel Hasse diagrams down except for in very rare situations. For a minimal element, this is one of the rare situations where you'd backtrack and go down the Hasse diagram. So, do we have an element that you can't go any further down from that element? If the answer is yes, that's your minimal element. What do you guys think? What could be a minimal element in this first Hasse diagram? Don't overthink it. Yeah, E. So E is your minimal element here. Now, that being said, any guesses who your greatest or your least elements are. And I like to use greatest and least elements mainly because I taught for years out of another book that called them that, but also because the first time you've heard the difference between maximal element and maximum element, it can just get confusing quickly. Okay? Any guesses who the greatest or maximum element might be? This is the element, and the definition here is this is the element that all other elements can reach going up the Hasse diagram. Turns out it is A. Why? Because if you start at E, you walk up your Hasse diagram, you get to A, and you can't go any further up. C, you go up to A, you can't get any further up. D, you get up to A, you can't get any further up. B, you get up to A, you can't get any further up. So that would be your greatest or maximum element. Now, what about for this guy, this least element or minimum element? Make sure I don't misspeak on you guys. Any guesses who might be the least element or the minimum element? This is the element that from this vertex in your Hasse diagram, you can travel up the Hasse diagram and reach everybody else in the Hasse diagram. Any guesses? Yep, it would be E again. So right here, this would be our minimal element. It is, if you prefer, think about it, the lowest element in your Hasse diagram. Your greatest element is your highest element in your Hasse diagram. Now, as soon as I say that, that's actually going to give you a bad idea in terms of finding your greatest and your least element, which is why I was trying hard not to say it. All right, so I am going, let's skip the middle one and go to the last Hasse diagram over here. Anybody have a guess what the maximal elements of this Hasse diagram might be? Or actually, let's just do the middle one. We can do that. Any guesses what the maximal elements of this Hasse diagram might be? So middle graph. The one looks like a, I don't know, diamond shaped on the bottom and a Y on top. So any guesses on maximal elements? Remember the definition of a maximal element or elements. You go up the Hasse diagram until you can't go any further, and yes, this is the key thing of this second example. You can have more than one maximal element. That is totally something that happens all the time. Both A and B are your maximal elements. Now, any guesses who your minimal element or elements might be? Yep, just G. Now this particular question for the next part actually threw it up on Poll Everywhere for us. Okay? I see that about half of you, actually a little more than half of you have already found it. So I'm going to go ahead and share this screen real quick. It only asked you for one thing. And the one thing it asked you, let me try to get it so it doesn't cover up. Excellent. The only thing it asked you is for this exact same picture, if you can spot the greatest element. And while you guys are spotting the greatest element, I'm going to go ahead and tell you that our least element is G, the same as our minimal element. All right, it looks like answers are stabilizing, so I'm going to stop sharing this screen with us. See what you guys thought. Oh my, there's answers all over the place. My concern is the people who selected C. All right, So, if you are looking for a greatest element on this guy, remember the key thing with the greatest element is there's nobody above your greatest element. So who are the only potentials for your greatest element? Well, the only potential candidates for a greatest element are elements that are already maximal elements. So the only options that we have is your greatest element could be A, it could be B, or it could not exist. Those are the only realistic options that we have here. Now, in terms of figuring out which of those answers it actually is, we have to go back to the formal definition of what the greatest element is. Well, the greatest element, oops, it's not scrolling. Come, scroll, thank you. Greatest element is the element that all the elements below your greatest element can get to it. Or it's not all of them below. It's all of the other elements actually in your building set. So in order to see if your greatest element exists, you have to make sure that every other element, every other vertex in your Hasse diagram, you can travel your edges and get from those other guys up to your potential greatest element. Well, here's the nice thing. If we try to go from G to one of the two maximal elements, we can totally get to both of them. E, you could totally get to both of them. F, you could totally get to both of them. Remember, you're going up the arrows. You can only go up the arrows. D, you could get to either of them. C, you could get to either of them. So right now, both A and B look like good candidates for your greatest element. Now, what if A was your greatest element? If A is your greatest element, everybody other than B, we already established, could travel up to A. But what about B? Can you travel between B and get over to A? Or vice versa is the next one we're going to check. So what do you guys think? Could we actually, in this Hasse diagram, travel between A and B? In other words, are A and B comparable is actually the buzzword. What do you guys think? Turns out they're not. And the reason they're not comparable is because you can't travel down an edge. So remember, in a Hasse diagram, there's an implicit direction. If the arrow is, in other words, you can only travel up your edge because there's really a direction on each of these edges. It was really an arrow that we just didn't bother putting the little arrowheads on. So if you put the little arrowheads on, notice if you start at B, you can't travel back to C and then up to A. It's not possible to be going the wrong direction on your arrow. Same deal, you can't travel from A over to B because you'd have to go in the wrong direction on your arrow. So what that means is your greatest element actually doesn't exist, and it doesn't exist actually any time you have more than one maximal element. If you're on a finite situation, in other words, you actually can draw out the complete picture for your Hasse diagram, you will always have at least one maximal and minimal element. But you don't always have your greatest and least elements. You don't have them if you have more than one maximal or more than one minimal element. So let's finish this last example. In this last example here, we actually have a grand total of 3 minimal elements. Those would be E, F, and G. So those are our minimal elements, which means if we do the same logic as in the second example, there would be no least element here. Wow, I can't spell least. Now, in terms of maximal elements, there's also more than one maximal element, and you can see that right here. Both A and B would be maximal elements, which means there's also no greatest element in this last example. Now, here's the ending question for us. Are there 3 maximal elements in that last Hasse diagram? Not 3, excuse me, 2 maximal elements. I was looking down here at minimal. Are there 2 maximal elements in this last Hasse diagram? What do you guys think? Did I pick up all the maximal elements, in other words? And the answer is actually no, there's one more maximal element. Can you guys find the last maximal element? Exactly. C is also a maximal element, and that is because from C, you cannot go any further up the graph. Same issue in the second example. Here, you can't go down any of these arrows, any of these edges that are attached to C. So this C is also considered maximal. Notice your maximal elements don't have to be the highest vertices in the graph. They just have to be essentially like if you're in a calculus class, those peaks and valleys that you look for your max and min. Same sort of idea here. You're looking for the points where you can't go any further up in your Hasse diagram. But the greatest and least elements is where you have one single maximal element or one single minimal element is sort of the distinction there. Okay. But that's it for this section. The only thing that we have left to talk about with Posets is going to be dealing with lattices and Boolean algebra, so we'll talk about that next time. We'll also go over the study guide for the final exam next time, which should be posted later today because I got a little bit behind in putting it together. Okay? So you'll see that stuff come up soon. I'll hang out for a little bit in case you guys have any questions, but that is it. We are done.